Good morning. Thanks for having me here and as part of this really interesting and exciting meeting. My name is Ty Foray. I'm from Hydrology and Atmospheric Sciences at the University of Arizona. If you haven't quite noticed, I'm not here in person. There is no one at this podium. In fact, I'm just outside of Burlington, Vermont, and by my reckoning, I am about 14 hours behind you. I know that some of you probably relate better if you can see the person who's speaking. In case that helps you, a number of people have described me as a handsome George Clooney. One last bit of background before we jump into the talk. Some people really benefit from having a talk outline. I don't really like them, but I'm told I should give one. I will begin my talk with a title. I'll follow along some somewhat rambling paths, and I'll try to give some conclusions at the end. The title of my talk is Who Cares and What Will It Cost? My goal is to explore some elements of where we go wrong in hydrologic analysis when we try to communicate our findings to the people who pay for or who are interested in our studies. This is really going to be a step back from the high-level talks that you've had in this session and will have continuing in this meeting. But I really think it's important to spend a little bit of time making sure that we stay on the same page as the people who will really use our science. Otherwise, frankly, I don't think our science will be worth very much. In describing the people who will use our predictions, I'm going to use some fairly general terms. One would be a decision maker, could be anyone basically making a decision based on our results, or a stakeholder, somebody who may not have the power to make a decision, but who is actually interested in the outcome of the analysis that's being supported. The key point here is that any decision has two elements. It has a forecast element. We're generally thinking about some kind of decision that's going to have an impact in the future, and therefore we have to forecast the future impacts of that decision. And it also has a valuation, and that valuation is strictly the domain of the decision maker, or more explicitly the stakeholder, who has to decide among possible outcomes to determine the relative value to them. That is, we might make multiple predictions, and only some of those predictions would be important to some stakeholders and some to others, and the actual predicted level of that outcome might have different values for different stakeholders. There's certainly nothing too challenging in that concept. Let's dig a little bit deeper. Essentially, what we can state that we're doing when we run models is we're taking some response or responses in the past up to the current time, and we're using those to make some forecast about these responses or other responses at some decision horizon, some later point in time. Essentially, this involves calibrating our model to the data that we have so that we can make some kind of informed prediction about the future course of events. The stakeholder comes in determining whether or not these predicted outcomes are favorable or not, or acceptable or not, or perhaps they'll even put them on some continuum of value based on that predicted outcome. For example, we may have a series of water levels or flows in rivers. In the past, we're using those to make some forecast that if we add another water user or we change the rate of water use, what will those flows be in the future, or some other water level or prediction that could be made from the model. The stakeholder, in the simplest sense, will decide that some range of predicted values, say water levels in a well, would be acceptable or would be high value, and some other range would be different. And of course, each stakeholder would make a different valuation. This version of the story is really simple, and this is often the way that we think of the use of models, or we explain the use of models to people who understand less about it than we do. But things become immediately more difficult if we think about using some of the ensemble techniques that we've talked about so far in this conference. What do we do if we have multiple models that, again, for ease of discussion, all have comparable fit to the existing data, but make very different predictions in the end? How do we advise a user or a stakeholder if some of these models end up in places that make them very happy and some end up in places that do not. To continue the story, I'd like to introduce two representative stakeholders. We have Jill, who's an optimist, and we have Jack, who's a pessimist, perhaps based on their previous experience with the outcome of walking up hills. Each of these stakeholders, for whatever reason, is going to bring different background to the question, and so they will view this question in a different way. How then should each of these stakeholders view an ensemble of models? I contend that Jill, being an optimist, she will naturally favor those models that support her foregone conclusion that things will turn out just fine. In contrast, Jack is going to focus on a different set of models. He will see those models that say there is some possibility that something will go wrong, and if those models are included in the ensemble of models, they will inform his decision. In particular, this kind of loss aversion is a natural part of decision making. It's hidden from us, it's hidden from most people anyway, but it can really drive the way that we view uncertain outcomes. So, as highly mathematically literate people, what do? Well, we inform Jack and Jill that while there are multiple possible outcomes, each outcome has a different probability based on the goodness of fit to the data that we have managed to collect in the present and those uncertainties that we have identified that affect the future. If we think carefully about it, both of those elements are pretty highly qualified. The data that we have are usually quite limited, both in number and in information content related to our predictions of interest. And the ensemble that we've constructed to represent uncertainty almost always misses something that could be quite relevant for the predictions of interest. So how should a rational decision maker look at this uncertain prediction that we're making? Well, that depends. If you're Jill, the weight of probability is supporting the outcome that you prefer. So our natural biases will make it very easy for us to look at those probabilities and say, we can comfortably discount those predictions that don't comport with our expectations or our desires, and feel like we're using a probabilistic argument to support our decision. If you're Jack, if you care about outliers, low probability outcomes that have a large negative impact, then you're going to be very focused on that low probability portion of the distribution, and you'll put much more emphasis on what's missing, the paucity of data or the incompleteness of our model ensemble. The end result is that, for very different reasons, both Jack and Jill will look at our probabilistic outcome and essentially not change their opinion. They will see the result that they want to see from the statistics. And the hard thing for us to understand as objective scientists is that this is a perfectly rational thing for them to do. In many ways, it's the right way for them to make decisions. Essentially, this is simply a statement of their different cost functions or utility functions. What we tell them statistically has different meaning depending upon how they're going to apply the information that we're providing. And I think we're missing an opportunity to take this into account when we do our analyses. Stated another way, I think that we're ignoring the fact that, as Kahneman said, people don't really make decisions based on statistics. They make them based on stories. And this has import for both the Jills and the Jacks of the world. The Jills to make sure that they're not overly confident or unrealistically confident based on statistics that may not be as strongly supportive as they think. And for Jack, of course, to help them to break away from an overemphasis on low probability, high risk outcomes. The challenge for us is, how do we address this need for stakeholder story-based decision making while maintaining some kind of statistical rigor in our analysis and some objectivity? And the answer, as the answer for all things seems to be, Bayes' theorem. Let's face it, Bayes' theorem is beautiful. It really is. Once you're a Bayesian, you never look back. You are a Bayesian for life. Everything really is wrapped up in this one simple equation. So why is it that people find it so confusing? Well, if you're confused about something these days, of course, the best thing to do is to go to Wikipedia. Wikipedia has a simple definition for Bayes, describing the probability of an event based on prior knowledge of conditions that might be related to the event. What could be clearer than that and more informative? Of course, in the same article, Wikipedia has another definition for Bayes, how a degree of belief expressed as probability should rationally change to account for availability of related evidence. It's getting a little bit more obscure, a little bit perhaps less easy to understand and apply, but if you understand Bayes, you still see that it is a perfectly reasonable definition, as is the third definition given in the same Wikipedia article, the use of conditional probability to formulate the relation of an updated posterior probability from a prior probability given evidence. At this point, both Jack and Jill are looking at us with concern, let's say. So let's take a moment to think about what Bayes means, what it means to us as scientists, what it means to Jack and Jill, and how maybe we can bring these things together in a bit better way to make better use of our science. Let's see if we can break down Bayes in a way that speaks to both you and me. We're going to start out by imagining everyone in the world in this rectangular box. We have 8 billion people just distributed within this box. Now we're going to take a random shape that represents some fraction of that population. And that's going to represent the probability that anyone in the world likes Vegemite. So at this point, it's about 0.004 population wide. We're also going to look at another population, a second arbitrary shape, those people who like peanut butter. This is about 10 times as high, the probability, 0.04. Now, we can also imagine that we could determine the number of people, or the probability that any person in the world likes both peanut butter and Vegemite, and that probability would be 0. But that doesn't make things very interesting. So let's imagine that there is some odd part of each of these areas in which people like both. In this case, if we imagine that there's about 100 million people in this overlapping area, then we have a probability that someone in the world likes both Vegemite and peanut butter of 0.015. So far, so good. But what do we do with this? Well, the other way we can look at this is, if we actually know that somebody likes Vegemite, then if we also know the probability that somebody likes Vegemite also likes peanut butter, then we can determine the probability of that overlapping region. We can do the same, of course, if we know that somebody likes peanut butter, and we also know the probability that somebody that likes peanut butter also likes Vegemite, and we can determine that blue area, that probability of A given B. So within that population, what's the probability of the overlap? And if we put all of this together, then we can use these different probabilities to determine whether or not somebody is likely to like, say, peanut butter, with or without the information that they like Vegemite. And we can express this multiple ways, and this equation up here really just says that same thing. The probability that somebody likes both is the probability that somebody likes, say, peanut butter, and multiply that by the probability that somebody likes peanut butter likes Vegemite, right? Or vice versa. So that's all very useful, maybe, if you can think of what to do with it, but where it really becomes useful is if we do a simple rearrangement of this, and then we can say, what is the probability that somebody likes Vegemite, given that they like peanut butter? And this then has that probability of liking peanut butter given that you like Vegemite, the probability that somebody likes Vegemite, and the probability that somebody likes peanut butter. But in fact, this isn't even the most useful way to look at Bayes, in my opinion. We need one more step. We're going to move the probability of A, the probability that somebody likes Vegemite, and we're going to break out this second term, this probability that somebody likes peanut butter given that they like Vegemite versus the overall probability that somebody likes peanut butter. Okay, so what does this mean for anyone? This can be stated simply as how much should you believe that something is going to happen with and without some evidence. So the left-hand side is the probability of some outcome A, whether that's some random person liking Vegemite or whether it's some bad outcome, given some other information. So in the case of Vegemite, how much should we change our opinion of whether or not somebody likes Vegemite, given that they've already told us that they like peanut butter? Or in the terms of a hydrologic outcome, how much should we expect some bad outcome, given some data that we've collected and some models that we've built? The right-hand side is our prior belief. So how much faith did we put in the outcome that somebody would like Vegemite, or would some bad outcome would occur before we collected these data or built these models? And the second term is really a way that we can put measurements into context. Measurements or models, or and models. And so that Bayes factor, that last term, is really a way to try to help us to understand how much we should be influenced by, say, a hydrologic analysis. And it allows us to go one step further, because it allows us to look at a well-constructed ensemble, one that really covers the range of possible outcomes or possible realities. And in that, we can say if we have some measurements, say in a water level in a well, or some stream flow, we can characterize from all of those possibilities what fraction of them actually give us these observations or agree reasonably well with these observations. That's the denominator. That tells us, of all the people in the world, how many like peanut butter to start with? How discriminatory, how rare is this observation? If it's not very rare, if every single model gives us the same water level, or every person in the world liked peanut butter, then it wouldn't be very valuable to collect those data. The numerator tells us the correlation between somebody liking peanut butter and somebody liking Vegemite. If this number is high, it means that that observation is a good indicator of the thing that we really care about. So in other words, if the outcome that interests us is highly correlated to some observed value in a well at some time, then that should be a highly informative piece of information to collect. But that's tempered by how many other possible realizations give us that same predicted observation. So really, if we can find a way to describe this to people, we can help them to understand, first of all, what we're doing. We're really informing how much they should change their opinion rather than telling them what their opinion should be. And secondly, it can put into context which observations we should be trying to collect and they should be paying for in order to give them the best information that is most relevant to the decisions that they need to make. So how do we address all of this in the context of storyline-driven decision-making and hydrologic analysis, multi-model analysis? Let's go back to the title. Who cares and what will it cost? Well, the first part is relatively easy, one would hope. Hopefully we know who the stakeholders, the range of stakeholders might be before we're building a model, because I think we can accept that no model is going to answer every question equally well. So we should really tailor our analyses toward the questions that will be asked using the models. Then we have the question of what will it cost. And in this sense, the stakeholders are essentially asking, what's it worth to do all of this analysis? How am I going to use your analysis to make better decisions? So I think we should recast this as, what is it worth? And more specifically, what is it worth to each stakeholder to have some evidence that might change their belief in the probability of their outcome of interest? Because frankly, if the stakeholders can say up front that no amount of analysis is really going to change their mind, then we're kind of tilting at windmills. On the other hand, if we can try to get some buy-in early on to say, how much would it change your opinion or change your decision if we can do an honest and objective analysis to show you that your concerns either are not well-founded or your hopes are well-founded, then we have something that we can really be working with. So how do we do that? Well, I think that the really important place to start is in how we build our ensembles. And in particular, if we take this from the point of view of a stakeholder, let's start with Jack, somebody that's concerned about an outlier. What's really important is to convince Jack that our ensemble actually includes the models that might end up leading to negative outcomes. And I call these advocacy models. We're essentially really looking for models that aren't necessarily the highest probability given the data that we have, but they are plausible models, all plausible models, that could end up in a place where Jack would be unhappy. And we want to use these to essentially represent Jack's concerns in the ensemble. At that point, if we can again get that kind of buy-in, then hopefully we have some chance to say, if we can discount these models by collecting the right data, would you update your concern about the added hydrologic stress, for example? Then the question becomes, well, which data should we collect? Here we have to have both the advocacy models and a very robust ensemble of models so that we can represent anything that we might measure and look for those data that are discriminatory, those data that have a high correlation with Jack's concerns, but also have a low probability of occurring for other reasons. It's not like everybody likes peanut butter. So in this looking for discriminatory data, if we take this as a very simple example, we're proposing one type of measurement that we could make at multiple times. We can start from Jack's concerns and collect those models of concern, and then look for some time at which we could make a measurement that would discriminate those models from other models. And if we choose this time here, we would say that if the data that we collect agrees with our models of concern, it is likely to disagree with other models, and therefore it would increase the likelihood of those models of concern, and vice versa. If the collected data does not agree with our models, then we have a collective sense that our concerns should be reduced in likelihood and expectation. Of course, Jill will have different outcomes of concern. She would be more interested in different models, and so we would really look for different times, in this case, at which we might be able to make measurements that would be discriminatory for Jill. In an ideal world, we might be able to find discriminatory data that actually help multiple stakeholders, and this might be a way that we could promote some collaboration, even if people's interests don't align. And that's the simple story from my point of view. It's taking into account the fact that people want to have stories that they can understand, seeing if we can represent those as scientific models within an ensemble, within a robust ensemble, and then looking for the data that can best test one set of hypotheses, their models of concern, against all other models. It's kind of a simple restatement of the scientific method, but I do believe that it takes a different approach to building model ensembles than we generally do, which is often really focused around identifying those models that best agree with the data that we happen to have at the moment. And I think we need to modify this by also looking for those models that have the biggest possible impact or the biggest possible opportunity to change stakeholders' minds.